Okay, today we're going to start looking at our new chapter on magnetism, and we'll start today by going through a little bit of history. It's believed that the Greeks, once again, just like electrostatics, they were the first to discover magnetism, and it was just by fluke that they happened to notice that certain black rocks in their area would attract nails and other kind of metal pieces. And they basically thought it was magical. There was some sort of magical rock, but it ended up being that those rocks just had magnetite in it, which is just an iron mineral that acts like a magnet. What they did do over the years, though, is find out that if you took a magnet, like a chunk of magnetic rock, and break it apart, you get smaller magnets. And probably by smashing them apart, they found like a little tiny sliver of a magnet. Let's suppose as they're breaking it, that little sliver falls into like a little mud puddle or something. They found that if it was floating on water, it would move a certain direction. So what they did is they invented the first compass. So compasses technically weren't invented until the Chinese invented them in about the 11th century or so, but there has always been over the years some sort of use of a compass to help us with direction. And the reason for it is our little compass acts like a little mini magnet. So we have a north and south part of a compass, and that's going to be angled a certain direction depending on wherever our magnetic field is of the Earth, the North Pole, South Pole, that type of thing. Okay, so with any magnet, we always call one end north, one end south, and all magnets will have that no matter how big they are. You keep breaking in smaller and smaller, all you're going to get is smaller magnets with both north and south poles. And law of magnetism, you guys should know this from before. Basically, like poles repel, opposite poles attract. So if you had two north poles next to each other, they're going to repel. A north and a south will attract. So pretty easy stuff there. One quick note before we look at a magnetic field. Most people assume that any kind of metal will stick to a magnet, and what happens is that's not indeed the case. There's only a few elements: iron, nickel, cadmium, and so on. There's only a handful that are known as ferromagnetic, which just basically means that they attract magnets or they can turn into magnets themselves. So a magnetic field then is very similar to what we talked about with an electrical charge. So when we had a positive charge, we said we had an electric field that went outwards from it based on having a positive charge near it. So the same thing sort of happens, except with a magnet, we can only get a magnetic field when we have both a north and a south. So it can either just be one magnet that has a magnetic field, or we could have like two magnets side by side. So let's suppose we have two that the north and south poles are a certain distance apart. We'll get magnetic field lines between those. So electrical charges, you only need one, and you get your electric field. Magnetic, we have to have the north and south. So we actually measure magnetic fields in Teslas, and we use the symbol B. I'm not sure why B is used, probably because it wasn't used for anything else, but we use the symbol B to indicate magnetic field, and it's a derived unit called Tesla, not derived unit, just sort of an invented unit, which there is really no ways of measuring magnetic field strength other than we know it's stronger, weaker. So it's based on how much it would twist a compass needle. So if you could have some sort of device measuring how much torque or twist is on a compass, that's how we would measure the electric field. So if you had a very weak magnetic field, the compass would barely move. So that'd be something like the Earth's magnetic field, right? It's not overly strong. We don't see things, metallic things flying through the air because the magnetic field's so strong. It's very weak, and you have to have a pretty delicate compass to be able to detect it. Something like a fridge magnet, still pretty weak, but obviously quite a bit stronger. And then if we had a super strong lab magnet that can pick up heavy objects, obviously we got stronger magnets. We'd say that'd be something like 2 Teslas. So let's figure out how we can draw magnetic field lines. So remember, we think of a compass as being like a mini magnet. So a compass will have a north and a south pole. Okay, so whichever direction the compass would be placed is going to help us indicate what the direction of the field is. So for example, if we had a north pole, south pole magnet like this, And if we took our little compass, with a compass, instead of drawing it as a magnet north-south, quite often what we'll do is just show an arrow pointing to the north, or sometimes they'll give you sort of a needle. They'll just have one end shaded as being the north end. There's lots of different ways of doing it. We'll stick, for this stuff, we'll stick to it as an arrow because it's easy and fast to draw. So the idea then is if the arrow is the north...
The warbird bus here is for students going...
So the north pole will indicate as the arrow. So if we took a magnet, and we put a compass nearby, so if we had a compass near the North Pole, right, the needle of the compass will point away from the north, right, because the north would repel, the south and the north would attract. So using that, that's how we're going to indicate the field lines. So we're going to say that our magnetic field will go away from the north, something like that. And then if we had our compass over here, the North Pole of the compass would get attracted to the south. So then we'd say our south magnetic field lines go inwards. And for one particular magnet, we basically get sort of these curvy magnetic field lines. So our field would look something like that, going around a compass. Or around a magnet, sorry. So let me just redo this a little bit clearer. So North Pole, South Pole around a magnet. Our field lines go away from the north towards the south. And they go both directions. Something like that. Okay, so outwards from the north, inwards to the south. So that's if you just had one magnet. If we ended up getting where we had, just like we did, remember with charges, we put a whole bunch of charges in a line, we can get straight field lines. The same sort of thing applies if we have a magnet, two magnets with a gap between them. We basically would get a straight magnetic field between the two. The edges would bulge a little bit, but just like we did with electric fields, as long as we're in between, they should be fairly straight. So our magnetic field, we indicate by B in this case, is going from the north to the south. William Gilbert, an English scientist back in the 1700s, 1800s, somewhere in there, he was the one that actually indicated that the Earth itself acts like a giant magnet. So what he did was he said, he pictures the Earth because it's spinning and so on. He basically says, think of the Earth as being one huge magnet from the North Pole to the South Pole. And what he said was, because our compass, if we have a compass on the Earth, it's going to point to the north, right? So our little compass will point north like that. So Gilbert came up with the idea that then our north part of the Earth would actually be the magnetic South Pole, and then the south part would actually be the north, just to match how the compass points. So magnetic poles show up as south and north. So our magnetic field lines then would go from the north towards the south. So if you kind of picture this as sort of being like a ball shape, it would just kind of go around the Earth in a curved manner from the north towards the south. And it would just kind of do that in every different direction. Okay? So what you got to be careful of is, in terms of a magnet, if I'm going to draw the Earth as sort of being a magnet, we have South Pole, North Pole, like that. But in terms of geography, our North Pole is off a bit because it's based on how the Earth rotates. So we'd actually have North Pole and South Pole, something like that for geography. So you got to be a little bit careful. So the first thing to remember is our magnetic north and south are reversed compared to our geographic north and south. And the only reason for that is it's based on how we define a compass and how we define field lines. So it has to be like that for it to match what our previous definition is. And also be careful that you notice the two poles don't line up. So our magnetic South Pole is not in the same location as our geographic north, and vice versa. So those are based on where the Earth spins. The magnetic poles are based more straight up and down of where the Earth's magnet location is. And so you have to realize that because they're different, our geometric North Pole and magnetic South Pole are roughly about 1,500 kilometers apart in the northern part of Canada. So if you had your compass, it's actually pointing towards the top of the Earth, not towards our geographic North Pole. So because of that, you have to take into account, and depending on where you are in Canada and so on, you'd have to adjust your angle a little bit, otherwise you might be going in the wrong direction. Obviously, if you're a long ways away from the North Pole, it wouldn't really matter because that slight angle isn't going to make much difference. And with the advent of GPS, all this has pretty much been eliminated because we don't really use compasses all that more. We just use actual satellite positioning. We talked a little bit about the field lines. So if you kind of imagine the Earth as sort of being like a peeled orange, so you have your orange sphere shape, and you have each slice of orange kind of makes those lines that run from the top to the bottom. Think of those as being like your field lines. So your slices of orange look sort of like that. So we're going to go from the North Pole, which is down at the bottom of the Earth. South magnetic would be at the top. So our field lines would go upwards, kind of like the lines of the orange. One last thing, just a point of interest, that our north and south magnetic poles, because our field lines are sort of going out from them and in from them, if you were to actually look at the very top of the Earth, the magnetic North Pole, we'd see these magnetic field lines going out from it, so you'd actually end up getting this hole or depression void at the North Pole. And the same thing would happen at the south, where the field lines go inwards. They'd all go inwards, so you get this sort of dimple or void of magnetic field lines. And it's due to those magnetic field lines, where those holes are, that where we get our northern lights. So in the North Pole, the Earth gathers electric charge and other radiation that comes from the sun, and that's where it sort of leaks into our atmosphere. So it goes through our magnetic field right at the top and the bottom of our two poles. And as they hit our atmosphere, depending on temperature and charge in the air and all those kind of things, we get what we get as call our northern lights or southern lights if you were in Australia. And that's all for today.